All right, we are right at the start time, 2 o'clock Eastern Standard Time, so we'll go ahead and begin. First off, good afternoon. I'm Jason Thomas, Portfolio Coordinator at America Makes, and I'll be your host for today's America Makes TRX webinar series. I know we still have some people logging in, so we'll get the housekeeping out of the way here. A little background on the TRX webinar series before I introduce our speakers. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium called the America Makes Technical Review and Exchange webinar series was created. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with a broader community. If you or your team are interested in presenting during the TRX webinar series, there will be a link to complete the request form at the end of our series today, or you can reach out to the America Makes TRX webinar series administrator, Jason Thomas, directly. A few important notes before we kick off the series. At the end of the presentation, there will be an opportunity for question and answer. If during the presentation you have a question, please submit it in the Q&A space on your WebEx screen, and I'll ask it during the Q&A session. I will do my best to get all of your questions answered. Today's webinar, is on insertion loss of 3D printed selectively metallized microstrip circuits on low loss dielectric with varied surface roughness. Without further ado, it is my pleasure to introduce Colby Hobart of Fortify and Mike Vinson of Averatek. With over 35 years of experience in product development and marketing electronics, Mike Vinson has been responsible for all aspects of product and process development activities and manufacturing operations. Today, Mike leads the commercialization of Averatek precursor catalytic ink, nanomaterials, and ink blocking materials. Prior to this, he served as program manager, products and services group at SRI International. Mike was also director of business development for semiconductor equipment, VP of sales and marketing, VP of business development, manager of applied R&D for Colk and Soft Industries, manager process engineering assembly interconnection lab at Texas Instruments Inc., and a manager at Abacus Wire Bond Engineering. Colby is an experienced radio frequency engineer in both the design and applications engineering areas. With 18 years of experience in the field, he has held positions with several subcontractor suppliers to the military prime contractors, performing work on various passive components for radar systems. New to the additive manufacturing market, Colby brings his breadth of experience in RF and radar to this space. His main focus in the RF applications role is to bridge the gap between the type of RF design engineer he has worked with for years and the enabling technology that brings relevant, low-loss RF materials to the additive manufacturing market. He very much enjoys the excitement of demonstrating to customers the enhanced antenna performance they can achieve through additive technology. Mike and Colby, I will now turn it over to you and your team.
Great. Thanks very much, Jason, for the introduction. So thanks everyone for coming today to listen to our webinar. We're going to be talking about microstrip circuits on low loss Rogers Radix material and the components that Fortify has printed and had metallized by Averatek to do some studies on surface roughness and those effects. So just to highlight a little bit about Fortify as a company, we manufacture a printer that is capable of 3D printing some highly specialized materials. And the printer prints, we'll talk a little bit more about, but photo-curable polymers, and specializes in a group of those polymers that are very high in viscosity and very high in filler content. The company is a full stack company, and when we say that, what we mean is not only did we develop and manufacture the printers, we also develop all of the software and firmware needed to operate those printers. And we are also a material science company developing materials. In fact, some of the founders like to say that we were a materials company first that was forced into developing a 3D printer capable of printing those materials since none existed on the market. Next slide, please. So a couple of the reasons this printer by Fortify is unique in what it can print for the range of photocurable polymers. One reason, it's not on this slide, but I'll mention, is the force of the z-axis plunge with the build plate can be up to 2,000 newtons, and that is important because of the very high viscosity materials that we want to print, and that is the highest force in class to thin out the material. So if you look at the print reservoir and the build plate above it being plunged on the z-axis, we work with materials sometimes due to that high filler content as thick as clay, and the build plate must plunge down at its 8.5 by 4-inch footprint and squish that material to a thickness of 75 micron. Well, really anywhere from 20 to 25 to 150 micron. For the purpose of the Rogers Radix we'll be discussing today, it is a 75 micron build layer. So that compresses to 75 micron, and then the projector, UV projector, flashes once, and all the white pixels that on the projector at 1080p will cure, and all the black pixels will not cure. And that works out to a 75 micron cubed little building block in the part that's being printed. So the high force is able to compress that high viscosity material, but also the fillers in that material are prone to settling. In most of these materials that we're working for, these really high filler content. And so every few layers that print, the liquid filled resin will circulate out of the print reservoir and back down into this continuous mixer, this heated, continuous moving mixer down below. And that stirs up all the fillers that have well, really, they haven't started to settle yet. That's the whole point. But it agitates all the fillers again to ensure that they are stirred up in the resin and that there's no settling during the print. And that guarantees homogeneous material that is cured at the time of print, and also isotropic material across the dielectric, which the RF engineers in the audience will know is of very high importance for the RF materials. Next slide, please. Here's a little rundown of some of these high viscosity, high filler content materials that Fortify is focused on printing today. As I mentioned, we've got that material science team constantly working on developing new materials. I think at this time next year, this slide will be a lot more busy. But to talk through some of this today, the first one is Radix. Like I said, the materials team works to develop our own in-house materials, but at the same time, we are partnered with several materials companies in the industry. And one of those is Rogers. And Rogers has developed this Radix material that is the first photocurable polymer that has good RF characteristics across the entire industry. It's the only one. It's by itself in the industry at this time. And Fortify are the only company that are able to print this material. So we'll be diving in a lot deeper on Radix. We also have an ESD material. We have a couple ESD materials, actually. The one shown is a solid material that is capable of the highest temperatures, operating temperatures in the industry for a 3D printable ESD material. So that's really, really good for like a holding tray for ESD sensitive components to be surface mounted onto circuit boards. It can go through a eutectic SMT oven and mount those components while protecting them from electroshock and damage in the future. ESD is a very important characteristic for circuit board assembly handling. And These trays are usually at 6 weeks or more lead time out in the industry. In the case of our ESD material, you can have a tray designed and print it the same day if it's fairly shallow, or print it overnight if it's not. I mean, the print time for the materials listed here is around 6 millimeters per hour today. So that's how you figure out if it fits into a same day or overnight type of print. HPA fits into the RF market as well. That's high purity alumina, 99.8% purity alumina with a 9.8 dielectric constant. So this is good for some of those high decay applications like dielectric resonator antennas or ceramic filter resonators. Also can be used for lensing applications similar to the Radix when you need a wider range of effective decays. But it's also got an operating temperature of 1750 C. So it's great for those high temperature applications like high speed projectiles and space applications. There's another ceramic in the hopper here, not displayed here, that's a 97% purity alumina. It's alumina silicate. That is developed specifically for its low shrink capabilities. So these ceramics start as a photopolymer heavily loaded with ceramic powder, enough polymer to print on the printer, and then they are loaded into a sintering oven that burns off all the polymer and sinters together the ceramic powder, so that you end up with the same characteristics that you'd have out of material characteristics that you've had out of a machined ceramic part, but with high resolution features that oftentimes would be impossible to machine, kind of like the image shown there. The TCDR material, third from the right, is a highly thermal conductivity material that can be printed with high resolution on these printers, just like the others. It's not electrically conductive. This is a material that you could submerge in a system that in this case, that's an example of something that maybe fluid would be passing through in a pipe and pulling high levels of heat out of the fluid. Again, something that can be designed and realized within a day. We also have a digital tooling product that's used for injection molding applications. Due to the magnetic aligning of fibers in the material, it is the highest strength 3D printable injection molding tooling product on the market. So using the magnets in the printer systems, the fibers can all be aligned to give it added strength in the axis of most importance during the injection molding process. And last on the right is the high temperature tooling material. So this is a material that can be printed for jigs and fixtures for high temperature applications. So all of these materials can be printed on one printer. If you have one printer, you can print all these materials with the Flux 1 printer. Or if you just need the RF centric materials like the Radix and the HPA, that could be done on a Flux Core printer, which is slightly lower cost than the one with the magnets. Next slide. Just a quick deep dive on the Radix material itself. This is the photopolymer material developed by Rogers and printed solely by Fortify. The dielectric constant of 2.8 is a nice number for be right in the range of a lot of circuit board materials. The dissipation factor of 0043 at 10 gigahertz and 0046 is certainly the lowest loss DF number on a high resolution 3D printable material today. Those were measured at 10 gigahertz and 24 gigahertz respectively, the 0046. And so we expect from our knowledge of low loss materials that if you drew a line through those two numbers on a linear DF versus frequency graph, that you should come pretty close to extrapolating how this performs in E-band and above. So we do get a lot of questions about how this works at the automotive 77 gigahertz range, and it should be a linear increase using those two numbers. The CTE of the material is 76 parts per million per degree C. So 3 to 4 times that of copper. So plated through holes are something that still need to be studied a little more in depth. But the prediction is that with a little bit heavier plating, that they should do okay over a reasonable operating temperature range. The moisture absorption of 0.08 weight percentage gain over 24 hours is extremely low. So this is on par with other Rogers low loss traditional materials that you'll buy in sheet form. Really important for RF because with moisture absorption comes very quick escalation in loss within a device. So that's a number I think everyone should pay attention to if they're looking at any other kind of 3D printable lower loss materials. And then the decomposition temperature where it sees 1% weight loss happens at 313 C. So the operating temperature we've been using is 250 C. There's probably a little bit of room there. And then outgassing it passed, the standard ASTM test there. So next slide, please. This slide shows traditionally where 3D printable materials land as far as dissipation factor and dielectric constant. Please note the dissipation factor is on a logarithmic scale. So you are escalating quickly as you travel from left to right on the graph. That's the only way we could really meaningfully fit all these materials on one plot. Can I get a next click here? And what we found here is that the photopolymers are all over a 0.01. If you draw a line down the middle of the graph, and thermoplastics are what fall to the left of the 0.01. And that's important because I would consider left of the line really about the extent of what you can call low loss. And the left of the line is all thermoplastics prior to the introduction of Rogers Radix. And what that means is low resolution 3D printing. So there's not much you can do with fine shapes and the thermoplastics. They're nice materials in sheet form. And they are 3D printable to low resolution shapes. The photopolymers, on the other hand, have been high loss traditionally. And then if we get another click here, we can see where the radix falls, and very low loss for a photopolymer. Actually, the lowest loss material on this chart, outperforming the thermoplastics. And this is, due to Rogers Corporation and their very in-depth knowledge of low loss materials dating back, way back a number of years. They've been the industry leader in low loss materials in the traditional format, which is going to be a thin sheet of material, typically copper clad and processed by a circuit board house. And they have come up with this formulation that is photo curable, which makes it 3D printable, but only on the Fortify machine. Next slide. Just talking real quick about insertion loss. Insertion loss is when you excite a device. You can look at it as a black box with power over a range of frequencies. Insertion loss is what's reported back as how much power got through the device and out the other side. And there's 4 components to that insertion loss. There's reflection loss, which is really return loss. So whatever amount of power was reflected back at you due to geometry changes and impedance changes in the device. Radiation loss, which is whatever amount of power can radiate out of the device. It doesn't happen much in waveguide or strip line, but in Microstrip, there's some radiation loss. And in other devices, there would be radiation loss. I mean, that's the goal of an antenna, but that's not what we're talking about here. Dielectric loss is that DF number we talked about on the Radix. Very critical to have low dielectric loss and keep the percentage of dielectric loss well below the percentage of metal loss. That's how you know you have a low loss dielectric. If dielectric loss starts to exceed that of the metal loss, then your system is just going to be high loss in general. And then ohmic loss, that's the loss in the conductor as it is applied to the dielectric, and that's very important. If we're going to go after a low loss dielectric and advertise that, we better not be losing a whole bunch of power in our conductor. And you'll see a lot of 3D printable devices with silver ink printed on them in different methods, whether it's inkjet or aerosol jet or dispensed from a syringe. And that silver ink, even when sintered by high temperatures, rarely achieves much over 40% of bulk conductivity of silver. So those lines are very lossy. And the goal here at Fortify is to work with people like Averatek who are putting down high conductivity metals. So they'll get into that later, why their metals are high conductivity and low in loss. Next slide, please. Next slide. So just a quick look at a cartoon of surface roughness. There's two important factors in surface roughness. A lot of times the companies working with the vendor foil are going to advertise a roughness number like RA or average roughness of a material. But it's also important to put out that the periodicity of that roughness is important as well. So when your peaks and valleys are very close together, you will have a higher loss than when they are stretched out. And we'll talk about that more later as well. So next slide. And the experiment designed here is a series of microstrips so we printed at Fortify with a 750 micron thick dielectric. The way these are printed all standing up on end, that is the thinnest nominal value we were comfortable with at the time of this print. We're always striving for thinner, but we use a 750 micron stage, and we printed pairs of microstrips that are 800 millimeters 200 millimeters and 50 millimeters long. So that's an 8-inch and a 2-inch line, and later we'll report loss per inch based on that. So what we did here was we printed a number of different orientations. There are a couple that are flat to the build plate that aren't shown, but if you just you see the ones that are laying down the long way, if those were tipped on their side, that would be flat to the build plate, or up on supports hovering above the build plate in the same orientation. And then perpendicular to the build plate, we did a number of different angles to kind of stretch out the periodicity of the layer lines. So there are some at 90 degrees and some at 0 degrees and several angles in between here. If you look close, those long triangles are really just an angle of that, 5/8 inch wide microstrip being held up by a long series of supports. Next slide. So I'd like to turn it over to Mike at Averatek now, and he's going to talk about how they went about metallizing these microstrip structures and some characteristics of those metals that they use.
This is Mike Vinson at Averatek. Thank you for joining us today. Next slide. Averatek has been in business for about 15 years now, and our business is advanced manufacturing processes and chemistries. We've mainly focused on PCBs, ultra high density and high performance printed circuit boards, as well as packaged substrates. The other areas that we've been working on more recently, though, include RF passives, which are antennas and waveguides in our case. We're doing some thermal structures for heat pipes and vapor chambers, as well as heterogeneous modules for heat transfer. And then we're working on 3D printed objects with Fortify and others. Next slide. Averatek is one of SRI International spinouts. So we're in good company here. We have companies like Intuitive Surgical, Siri, which was a company before it was acquired by Apple and became the well-known voice engine that's in the Apple devices. And many others here that have been developed. In the materials area, though, Averatek is one of the principal spinouts there at SRI. Thank you. Next slide, please. So here we have an example. We have a video here of how we're patterned onto an antenna, which was a cylinder. This was for a GPS antenna. This was our first attempt at 3D patterning. So you can see the laser drawing the pattern into the catalyst. We'll talk a little bit more about that later. And then once we have the catalyst cured, we can then plate up with the electroless copper and then the electrolytic copper to perform the circuit. Next slide, please. So for the three-dimensional additive electronics, we would first start off with dipping the part into our LMI ink. That's our proprietary material that we've developed. We dry the solvent from the ink at a low temperature, and then we selectively cure the ink with the CO2 laser at low power, which was the video that you saw before, where it's curing only in the areas where the laser strikes the surface. After that, we remove the uncured portion, and LMI is a good ink for this because it is uniquely cured by heat. After that, we plate with the electroless and we plate with the electrolytic. In the case of the ceramic that we saw earlier, we cut that to length and we make electrical connections with solder for testing. Next slide, please. So our enabling chemistry here is the LMI liquid metal ink. Next slide. So our liquid metal ink is very unique in the industry. It's a solvent-based ink. It's non-aqueous. That enables a lot of things for low-cost manufacturing and additive manufacturing. It'll conform to any 3D surface on a nanometer scale. So this ink, if it's poured into a ceramic or coated onto a ceramic, it will penetrate all of the pores in there. We've worked with things like catalytic converters, where deep down inside the converter, there are a lot of pores. We found after doing cross-sectioning that the palladium was deposited on all surfaces and areas in there. At the end, after it's cured, it's very dense. It's a fully packed atomic film, and it's also very, very thin. It's only a few nanometers thick. The LMI can be formulated for different metals and their alloys. Primarily, though, for this, we're using palladium, which is acting as a catalyst for the electroless plating of other metals. Next slide. So a demonstration of that is we have the standard process for depositing a catalyst and then plating up with electrolysis on the left. We can see that the catalyst is not very dense. It's larger particles. They're usually deposited in an aqueous fashion, put down with some liquid and then developed there. And then the electrolysis, when it plates up, it's not very dense at the beginning. With the Averatek, you can see at the upper right-hand corner, that's a TEM, and the thickness of that is around the order of magnitude of 5 nanometers thick. It's in silicon. It's being put on top of silicon at this on that one, and then cross section so that we can see the thickness of the plating itself. When we do that, we get a very dense and thin coating of copper that we can electrolysely plate on top of that. Other metals as well can be electrolysely deposited, but copper is the most popular right now. And that's very dense, so that with only 100 or 200 nanometers thick of copper, we then form a cathode that allows us to plate up, electroplate up thicker layers of copper with electroplating. Next slide, please. The other key part of this equation is the laser that we're using. We chose a Keyence laser. It is designed and developed for patterning on 3D objects. It was originally developed for scribing logos and such on various objects for manufacturers. It'll handle almost any 3D object we put in there. Its surface topography is defined by the STI file that we submit to it. So we could have a cone or a hemisphere or parabolic shape. a double saddle shape, a number of different shapes that we could use to create a pattern on them with the 3D lasing capability. It does this by adjusting the focal point of the laser up and down, and it has a fairly large envelope that we can work with. Next slide, please. So this is an example of patterning onto a plastic material. This is a molded plastic that Rogers has developed. To do it all the way around the part, we need to index it because the laser is a line of sight tool. So when we've patterned it in one area, then we turn it around and then pattern the next adjacent area. As long as we carefully align these parts, it's very repeatable and very reproducible. And the parts you see on the right-hand side are the ones that we've electrolytically and then electroplated with on top of the fully cured catalyst. It's important to note that this is fully additive. There's none of these metals are removed after they've been cured and plated. So there's not like a foil on top of this that we began with. Also, in this case, it's directly deposited on the TMM material. There's no adhesive layer or any other layer that needs to be deposited before putting the metal on. Next slide, please. So with the Rogers Radix, we've done the same process on the Radix with slightly different parameters. But again, we've deposited the metal directly on the Radix material without using any kind of adhesive layer or tie layer underneath the metal strips. This pattern was developed so that we could test the adhesion on the Radix. Next slide, please. So when we look at a cross section, one of the things we're going to be talking about today is the roughness of the material. The roughness of the copper is directly related to the roughness of the substrate. So if we have an RA of 6 on the substrate, the bottom surface of the copper will also be a 6. The bigger peaks are reflected on the top surface of the copper because it gets some smoothing and filling. We can enhance this smoothing and filling further if we want to with changing plating parameters. But what you're seeing here is pretty typical for 40 micron thick copper on Radix. You can also see in the Radix sample here that it was printed in a 90-degree format. So you can see the layers running up and down here so that it was basically turned on its side to do the patterning and printing. Next slide, please. So the materials that we've evaluated with this 3D printing so far are the Fortify materials, the Radix, the HPA, and we're also looking in the future at digital tooling material. The molded or cast or machined 3D objects that we've worked with are the Rogers TMM, like the white cones that you saw before, the alumina ceramic, which was the ceramic rod that you saw, and we're working right now with ceramic composite. It's important to note that the HPA and the alumina ceramic process almost identically with the laser process. The plated metals that we're working with right now primarily are copper, palladium, and platinum in the electrolysis category. So that's the very thin 200 nanometer layer that we're putting down first. And then the electrolytic metals that will plate up to the thickness of the trace that we need are the copper, the platinum, and the gold. There are other metals that can be electrolysely plated and electrolytically plated, and we're compatible with most of those, but these are the ones that we're working on right now. Next slide, please.
All right, this is Colby. I'm going to be taking back over here to discuss the rest of the experiment after we got the parts back from Mike and his team over at Averatek. Really nice looking copper on the parts. So what we did next over at Fortify is we used our laser profilometry tool. It's a Keyence one-shot 3D VR is the name of the tool. And what that does is it allows us to measure in a bunch of different ways surface roughness of components. So I moved over from the signal trace slightly over onto the dielectric, and I took surface roughness measurements of the dielectric on every variant of microstrip pairs that we had printed and had metallized by Averatek. I opted to measure 1 by 1 centimeter squares and take a full profile of that area, just because some of the patterning and the roughness didn't seem to vary along a line as much as in an area, and I wanted to capture a true average of roughness. So what I did is I took 3 places per sample and measured these size swatches, and then I took the average of the 3 squares, and that's what is reported here in the chart to the right. So as far as samples that were printed with the broad wall parallel to the build plate, I had one where the signal was facing the film. So that gave a real smooth, the smoothest possible surface finish coming off the Fortify printer without post-processing, polishing, or anything like that. There was none of that post-processing in this experiment. I had another where the signal was facing the film, but the microstrip slab was suspended on what we call supports. Supports are these little, well, you saw them in a picture earlier, but they're these little cylindrical beams coming up from the build plate, from a little raft on the build plate, suspending the microstrip above the build plate. What's nice about the supports is that they help guarantee uniform thickness of the part if it's being built against the build plate or parallel to the build plate, because there is some self-leveling, very small amount of self-leveling that happens between the build plate and the reservoir or the film. However, there's a downside to printing on supports, and that is that as you remove the supports, you would have to sand them flush to get a really uniform surface there. I opted not to sand them, and so we printed the ground copper over a surface that looks kind of like a Lego, but the bumps are pretty close to the surface of the slab. So maybe these little like 100 micron bumps, that provides a little bit harder to anticipate impedance there. And then we did one where the signal was facing the build plate, and we have multiple build plates in house. We opted to use the rougher, more standard build plate, and that one shows a 9.2 micron RA, whereas the film facing ones show about a 1 micron RA. Now, when we go perpendicular to the build plate and print at various angles, remember we're printing at 75 micron layers. So the more we tilt the sample, the more kind of stretched out the distance between layers is. And at a 0 degree print, the layers are stacked from left to right across the transmission line. And at a 90 degree print, the layers are stacked 75 microns apart running up the transmission line. So this is the best way for us to just organically create different surface roughnesses with different periodicities coming off the printer. We could have done some things to artificially create different surface roughnesses, but the point of the experiment was to look at roughnesses as printed, so what customers can expect when they're printing parts. And on the perpendicular samples, we ranged from 2.8 micron to 5.3 micron average RA, and that kind of increases as the build angle increases from left to right. There's a little glitch in that line there, 40 to 70, but for the most part, that increases over time. That's probably just our ability to measure these surface roughnesses accurately. Next slide, please. Oh, one back. I'm sorry. Just looking at the pictures here, that's a picture coming off of the laser profilometer, and you can see how smooth that looks for the film side at the 0.9 RA and versus the build plate side at the 9.2 RA. Thanks. Next slide. Took all these samples after the profilometry down to Rogers, who graciously agreed to run some measurements for us in their nice intercontinental microwave W7000 fixture. And this is a fixture that is built to measure microstrips of various kinds. It's a pretty flexible fixture, which is really nice. It drops a little probe down onto the ground, and it's got some surround ground either underneath for standard microstrip or on top for like a coplanar waveguide launch style microstrip. It handles both and handles it very well. So the system is calibrated as you typically would for a network analyzer from the ends of the SMAs to each other. Actually, in this case, this was a 2.4 millimeter connection. This can actually measure up higher in frequency than our microstrips were designed for. And then the fixture becomes part of the measurement. So that's the whole point of this 8-inch and 2-inch lines, so that we can measure an 8-inch line, measure a 2-inch line. The 2 inches, long enough to give us good propagation coming out of the fixture. Let that wave kind of smooth out before it goes back into the fixture, so that we don't have any weird resonances there. And then essentially we subtract the insertion loss in dB of the 2-inch line from the 8-inch line and divide by 6. And we have a loss per inch metric per a given print orientation. So 2-inch and 8-inch line for every orientation were measured using this fixture. Next slide. So we'll just talk about results here. I separated the parallel to build plate varieties from the perpendicular to build plate varieties. I guess a little trade-off there in whether to separate them from the other, but what we see here on the green line was using Rogers loss prediction software, which they've proven out over time to be very accurate. We plugged in a 2.8 DK and a loss tangent of 0.004. Slight miscommunication when we were doing this simulation. It should have been a 0.043 we plugged in. We used 0.004 and perfectly smooth copper. So some ideal, perfectly smooth, no roughness copper. And that presents itself in the green line here. And then with the other lines here, we see the parallel to build plate. Supports sample, which I said had that kind of Lego shaped backplane, kind of hard to predict. It's actually a constantly changing impedance along the line to a small amount. It actually performed pretty well. But I think the important part of this output chart here is to separate the red line there. Ignore the red line. And we're looking at the very smoothest sample we could print and the very roughest sample we could print. And this is the most important result, is that those two are, I would say, exactly overlain through 10 gigahertz. And then you can see that the smoother result actually becomes slightly more lossy than the rougher result, which is odd, and you could probably attribute to measurement error or / noise in the system there. As you go higher in frequency, it's harder to measure this thing. But exactly the same through 10 gigahertz. And if the rougher one had taken off as more lossy, then I would say, probably the roughness is affecting that loss tangent, but that loss measurement. But really, we're looking at the same result. And that's very surprising, right? I mean, a 0.9 micron RA and a 9.2 micron RA on vendor foil. If we were printing and etching these in a board shop and the vendor foil showed up with those measurements, we would expect quite a bit more loss, definitely discernible on this plot. But we don't see that. And what that says is that the periodicity of the roughness coming off the Fortify printer is wide enough so that the roughness difference does not make a difference in loss. So that's very important. So if you're looking at a part printed by Fortify and the copper looks rough, the fact that those peaks and valleys are so stretched out compared to what you'd find on a treated vendor foil is essentially telling you not to have a concern over that. And very excited about this result shown on this slide. Next slide, please. Again, so this slide deals with all those perpendicular varieties. We printed 5 varieties here, and this time the Rogers MWI approximation simulation, which should be very accurate for a perfectly smooth copper, is shown in red, and the rest are very tightly grouped. We've got one outlier, which is the smoothest copper that we had, and it's showing it, far less lossy than the others. I'm going to say definitely a measurement error there, based on the previous slide and this slide being tightly grouped on all the other roughnesses. There's something going on with that outlier, but I wanted to include it because it is data, and we should address that. So again, we're looking at, slightly less lossy than an ideal case of perfectly smooth copper on a comparable dielectric. At 10 gigahertz, you're looking at slightly better than 1/4 of a dB per inch, which is a very respectable number. And this is showing that when we take Rogers low loss dielectric, they worked so hard to create this 3D printable low loss dielectric, and we pair that with Fortify's roughness coming off the printer and Averatek's metallization process for that high conductivity copper that really saves the day for showing off this low loss dielectric. We've got a very respectable device as in total loss on a microstrip. So the low loss dielectric is absolutely not going to waste. The other 2 components of the periodicity of our roughness at Fortify and that high conductivity copper from Averatek are the other 2 pieces in this puzzle. It all comes together as a 3-part system, and we've got some real low loss RF devices here. I think that's all, right?
All right. Excuse me. Thank you, gentlemen. That was a great presentation. We'll now head into the Q&A session. If you do have questions for our presenters and you have not done so already, please go ahead and type them into the Q&A space. I have a couple of questions here to get started with. So how thick can you make the metal on these parts?
That's a good question. These are fully additive metals so that we can plate them up to whatever thickness the customer would like. Because they're fully additive, we can't get very high aspect ratios, but we can get decent aspect ratios so that the height to the width is relatively good. But typically we plate up around 30 microns or 1 ounce copper in that range. Half ounce, 1/4 ounce are doable. But we can also do extremely thin metals, such as 100 or 200 nanometers, when those kind of resistances in the metals are sought.
Okay, I was just going to ask you about the thin walls. I think that's a lot of people are very interested in that area today. Let's see. So another question: how large of a part can you handle?
So I think as Colby mentioned, their plate was 4 inches by 8 inches. Is that right, Colby?
Yeah, 4.5, but yeah.
Okay, and for the laser that we're using right now, it has a 4 inch by 4 inch by 1.5 inch working envelope. So the z-axis is 1.5 inch. So that kind of defines what we're working with today. We can take larger parts and do a type of 5D process where we're actually moving the part underneath the laser and then moving to different areas and work with the larger part. And also Keyence makes larger area lasers that we can work with to make larger parts.
Okay, great. And so how would the results change for different dielectric thicknesses?
That's a very good question. I'll take that one. So essentially, the thicker the dielectric that we print, the lower the frequency range we're able to measure over is one aspect, but also the thicker dielectric that is printed, the lower the percentage of total loss that's attributed to that ohmic or metallic loss that I presented on an earlier slide. So I would consider 750 micron slabs, which are 30 mil for the A and D people, to be somewhat middle ground as far as what people are using for microstrip lines today. There's a lot of stuff on 60 mil or even double that. But there's also some, very thin microstrips for form-fitting purposes. Really, the microstrip designer is probably going to use as thick as they can for that application for routing and fitting in the thickness box because of that fact that the metal losses really dive the thicker you go. So if your goal, though, was to really characterize and make the difference in metal roughness as inward facing toward the ground really stand out, you would want to develop on the thinnest dielectric you could. And also that would allow you to characterize up to higher frequencies. So we noticed during testing that our frequency limitation for the measurements, it got noisy between 10 and 20 gigahertz, but above 20 gigahertz, there was some moding there, and that kind of made the results above 20 not very valid. And so a thinner dielectric would allow us or a microstrip designer to go up higher in frequency, which could be important. But also, I wanted to print on as thin of a dielectric as I could in order to really make those results of different roughnesses stand out against each other. And we were only comfortable today printing with those big, long structures standing off the build plate at about 750 micron. I would be interested in repeating the experiment sometime at, say, 20 mil or 10 mil, like a 250 micron. That would be excellent. That would really make the results contrast. However, given that chart that we showed with the roughest sample and the thinnest sample exactly on top of each other through 10 gigahertz, I'm quite confident that going thinner will prove the same, that our periodicity and our roughness makes it such that going rough has essentially no effect on the insertion loss of the system.
All right, great answer. Thank you, Colby. All right, so I think that's all the questions that we have for today. So that's going to wrap today's TRX webinar. I just want to once again thank Mike and Colby and the whole team. This has been great working with you guys. I think it was a great webinar. If any of our attendees have further questions for the presenters, you can reach out to them directly. We have their contact information here on the screen. And just another reminder, if you think you or your organization is interested in sharing on the TRX webinar series, you can fill out the form that is going to follow the presentation, or you can reach out to myself, Jason Thomas, at jason.thomas@ncdmm.org. Thanks again, everyone, and have a great day.
Thanks, Jason.
Thank you, Jason. Thanks, Colby.